So here we have the MTMC-16 virtual computer. This is a computer designed for education and fun. It has all the things that you would expect from a real computer, including registers that most of the computation is done in, 4 kilobytes of memory, which, once upon a time, that was what we had. But today we're kind of spoiled. We have a video display similar to a Game Boy for color with a gamepad to control any games we run on it. We have a text console where we can interact with the computer, load and run programs. And then we have a file explorer on the right where we can find files, open files, edit files, all that. As you can see, we don't have any files in our home directory at the moment. This is a fresh install. So let's see what we can do with this computer. So this being an educational computer is the intent. It's also a toy, so we can have fun with it. But being an educational computer, we can run assembly straight from the command line, which is kind of crazy. But it lets us see what's going on, right? So we've got all these registers here, T0 through T5, A0 through A3. Now T0 is actually the general purpose registers, while the A's are arguments for function passing. So it's got special registers just for C functions, and return value, return address. Of course, those are all intended for jumping around in C functions, and things like the program counter. We can't really mess with that because that is the program execution. At least not directly. We can change it, but let's use the T registers. They're 16-bit because it's a 16-bit computer, and you can see 4 nibbles with the bits light up, like 4096 here is lit. So we're going to load, let's say, load integer into T0. This is assembly, so when we're loading, we put the thing that we're going to load into first, and then we put the value. So we're going to put 42, secret to life, the universe, and everything. All right, and we can see we have 42 in T0. We can do it again. Let's put 10 in T1. And now we can run the assembly code to add T1 to T0. And you can see again, we're putting the thing that it's going to first and the other value second. So add, and we can see in T0, we now have 52. Awesome. And what can we do with that value? We can then store it back to memory. So let's do store word. And here's where assembly throws us a curve. It goes the opposite direction now. So we're going to take T0 and put it in memory location, what's that? 11. Yeah, let's word align here, 12. All right, so we're going to send word, location 12. Bam, location 12. Now, this is hexadecimal that we're looking at here. In fact, you'll notice that we're in a dynamic mode. Let's move over to hexadecimal. We can actually change the view. So this is hexadecimal. If we change it to decimal, we can see that it's 52. So we can be sure that our value got stored. Now, I'm going to put it back to dynamic mode because I'm going to show you what this is for. Now, you might have noticed there's a sys exit here, like as if that was a instruction. That's because it is. We're going to come over here, we're going to create a new file. So we've got a couple types. We're going to do assembly language, and we're going to say hello, because we're going to say hello world. So hello. And then we need a data section. That's where our data goes in any assembly program. And we're going to label hello and have a string, hello world. Don't forget our new line. And then a text section where our code goes. And we're going to start with a load. Oh, no, actually I want a load address to, let's see here. We're going to load it to A0 because that's going to be important for our system call. It's an argument. And then hello. And then we're going to call sys and w string. So that's going to write string to the console. And then sys exit to exit the program. All right, we'll save that. And we will say, now, of course, our program's not ready to run. We have to assemble it. So we're going to run the assembler, asm hello.asm, and output a binary called hello. And we run hello, and we can see hello world. Fantastic, right? Now, we saw that run. We can see in our memory that the instructions are here. The load A0, now it's LI instead of LA. LA is a alias. We can actually change this to LI and we'll get the same result. And that's just because I means integer and A means address. Address is an integer, but we try not to confuse ourselves, so the alias exists. So then we see it loads 8. Well, where's 8? 8. So 8 is somewhere here. Interesting. Now it looks like we're missing 2 bytes. You might have noticed, right? There should be H and E. And in fact, if we go to string, we can actually see hello, and we can see that that is position 8. The reason why we're seeing this load word register here is because the execution has gotten to this point, and so it's trying to interpret it as an instruction. But that 8, that is pointing to the location in memory that hello world is at. And we can see that more clearly if, rather than running the program, we load the program into memory. So this loads it but doesn't execute it. You can see that our execution pointer has gone back to 0. That's the program counter here. And it's lit up here to let us know this is the instruction that is about to be executed. And interestingly, you might have noticed that it also lit up over here in the assembly. So that's interesting. Let's take a look at what that is. All right, so we have the load instructions, and then let's get us back to dynamic mode. There we go. So in dynamic mode, we can see we have instructions and then a string, hello world. And so 8, we can now clearly see points here. So let's actually step into this. So that runs the load 8 instruction. If we hover over A0 here and the 8 value, you can see that the location here lights up. So it's telling us exactly where that location is pointing. So then we can see that the first instruction executed, and we are now at the syscall for write string to the console. And syscall is the underlying operating system. Sort of like DOS had various services. MTOS, the Montana operating system, is or Montana State operating system, excuse me, is writing to the console when we ask it to. So whatever we put in A0, it's going to try and write that string, and it knows how big string is based on that null terminator here. So when it reaches that 0, and let's look at this in hex, we can see it's actually a 0. So when it reaches that 0, it knows the string is done. That is how strings work in C and how they work in this computer. So we can see that we have a pointer to 8, and we're about to make the syscall. So let's step, and we can see we get hello world. And we're now at sysexit, which we can run sysexit, but it's not going to do much since we're stepping through. It just stops execution, and we're not really executing. We're just stepping through the program one step at a time. But what's cool is, do we think that was neat, writing the string? Well, we can go back a step, and you'll notice that the pointer went back to write string, and we're going to run it again, and we get another hello world. And we can keep doing that. Yeah, you know, like as if there wasn't a loop. Okay, and you know, if we want to be silly here, what we could do is we could say loop, and then jump, and jump, loop. Doesn't have any suggestions for me on that. Interesting. All right, so let's assemble again and run hello. Boom. And it's just going to keep going until we stop the program. You can see it wrote out quite a bit before we stopped it, and we just hit the pause button up there. But let's load it and step through it and see what was going on. So again, we load hello pointer into A0, and you'll notice the pointer has moved now because we added more instructions, so the data is a little further out, so it's now at 10. So let's step that, and you'll see that again we're pointing to the right location for hello world, and then we'll let it write out hello world, and then you'll notice that we're at this jump instruction for loop. So step, and we have jumped back to line 6, and you'll notice that it says jump 0 or 0. 0 is here, so it jumped exactly where we said it was. We can, do things here like we can change our program. So load T0. We want to counter, right? So T0. And let's say we want to print it 5 times. Okay, so then every time we print it, let's decrement li, and let's do a test. So if equals, so if T0 equals 0, now here's the thing, we're going to say if the test flag, so the test flag is set to 1 if this matches. So if T0 equals 0, we're going to get a 1, and if it does not match 0, we're going to get a 0. So we want to jump not 0. Jump not 0 is basically saying jump if true, and jump 0 would be jump if false. So if actually we want to jump if false, right? Because as long as it's not 0, we want to keep going. All right. So let's try it and see if we got it working. Oh, register not writable, LI. What line? Line 9. I screwed something up. Decrement, LI. T0. That's a little better. All right, so let's run it. And we can see we got it 5 times. And we can load and see what's happening. So 5 goes into T0, step again. A0 gets 18 now, where hello world is. And then we get to here, and T0 is going to be decremented, default by 1. So if we step again, we can see T0 is now 4, step. And now, if this flag is 1, it will not jump, but if it is 0, it will jump. So it is 0, so we expect it to jump. All right, and we can see, if we go through, it's going to keep decrementing the T0 to 1. All right, so this is the last loop through. So again, load hello, write string, decrement T0, and T0 is now 0. So now when we run our test, is T0 equal to 0? Yes, it is. And there we go. We have a flag that is 1, and so when we test if it's 0, it will not jump. And we get to our sysexit. And that's how we get exactly 5 printed out. Okay, cool. So that's a lot of fun. What else can we do with this? Well, there's a lot of programs included. So if we go under source code here, we can see there's utilities like cd, echo, ls. So I could always have just done echo hi, or I can do, and you can see the program actually loaded and ran. This wasn't just, in fact, let's slow the computer down. Let's take a look. All right, echo hi. And we can see that and make sure that something was passed by testing if A0, which is how we pass in the string, is not 0, and the hi is passed in from 16. So A0 was pointing to, A0 was pointing to 14. That's here. This is what gets me in trouble, because I let the program run, and then I expect that everything will stay the same, and it won't, right? So not equals A0. So A0 is, oh, right. So yeah, A0 is going to be 0. And what we actually need it to be, right. So that's the one downside. So what we can expect to happen is that when echo high is passed, high will be loaded into 16 here. A0 will get 16, and then it will make sure that A0 is not 0, so that something is passed in, and then if it's not 0, it exits, goes all the way to the end of the program, to here. Oh no, it looks like it loads. Oh, it just loads a new line. That explains it. Okay, so let's watch it. At 1 hertz, it'll be 1 step per second. So let's watch that A0. All right, A0, 16. Yeah, so we can see it's pointing to the high. And now it changed to 14 for the next step. All right, so echo is just a normal program. LS, just normal program. Where are we? We are... Oh, okay. So we are in utils. I'm not sure what's going on there. Oh, I know what's going on. We are too slow. Let's bring it back up. All right, so ls pwd, and we can of course ls bin and see all the compiled programs. So let's do something fun. Let's run a basic graphical program, and this lets us use the arrow keys to move the ant on the screen. Well, that's kind of cool, and I don't think these do anything. That's neat. What else can we do? There is a snake game. Who doesn't love snake? All right. And we can eat the pellets and that get bigger. Look at that. Fantastic game of snake. Oh no, oh no, crash. All right, game over, man, game over. And we can see that all the source code for these is in the games directory, including this one called fish dish. What's that? Let's take a look. Fish dish. Fish dish. Seem to be a fish. Okay. All right. Ah! There's a shark. Oh my goodness. Oh my goodness. Okay. All right. Look out. There's a shark. Okay. All right. Looks like a neat little demo. Okay. Let's stop that and let's run something else. Wumpus. Wumpus. Hunt the Wumpus. The hunt is about to begin. Very cool. All right. Instructions tells us how to hunt the Wumpus. And this appears to be a text-based adventure, right? So we're in room 3, and there are tunnels leading to other rooms. So we could say move to room 4. And it says bats are nearby. Well, I wonder if we'll run into them. So let's move to room 5 and see if we run into them. Ah, bats got us. We are now in room 14, Elsewheresville. So we can try moving to 15. Nothing in here. 16. All right. Feel a draft. Oh, maybe there's a pit nearby. Is it in 17 or 20? Let's see. It isn't in there, but it's in 18. Oh, there we go. I lost. All right, very neat. And that is a quick review of the MTMC, the Montana Mini Computer from Montana State University. Download it today and check it out.